Hi, my name is Julia Silye, and I'm a data scientist and software engineer at RStudio. And today, in this screencast, which is about a bit more advanced topics, we are going to use this week's Tidy Tuesday dataset on board game ratings. And we are going to train the model to predict the rating of the board game from data about its gameplay and what kind of game it is and whatnot. We are going to spend a little bit more time on feature engineering and talk about how you can use tidy models, of course, for many of the normal basic kind of feature engineering steps. But if you have more custom needs, Tidy Models offers extensibility, and so we're going to talk about how to do that we'll pick some of these characteristics of the board games and be able to build a model. It's a pretty big data set, good size with it's rectangular data, and so that's a pretty good fit for XGBoost, and it's I haven't done much XGBoost, since this past summer when we was like all XGBoost all the time using the sliced data sets that I did back then. So we'll return to XGBoost after time away.
All right, let's get started. We are going to look at this data on board games, and this is a data set where, like I said in the intro, we're going to spend a little bit more time doing some feature engineering, some slightly, you could think of it as like custom feature engineering here. And let's get these data sets. So there's two data sets as part of Tidy Tuesday this week. The ratings data set, which has name, an ID, year, and this average rating. There's this Bayes average rating, which is pretty interesting because if you notice, some of the games are rated by, that's still that's still a lot, right? But I bet some of the games are so look, these are only rated by like 30 people. So they've probably used like empirical Bayes here to like this is the average, and if you are like 5.5, 1 or 2 must be the average. And so in the Bayes average, someone has gone to the trouble of saying like let's use empirical Bayes to shrink values towards the mean if we don't have that many measurements of what the rating is. But so that's super interesting. I think I'm just gonna look at the average here, which is the average rating. Like maybe this would be a better value to use perhaps, but I feel like then you've got a little bit of like it's more complex, so I'm not going to do that today. So we've got the ratings. Now we've got the details. So in the details, we can link this up by the ID, and we have like year published, and then like a lot of information about the gameplay. Minimum players, maximum players, playing time, min play time, max play time, minimum age, and then this category. Then there's a lot of interesting things over here. The category, like is it a card game, an economic game, the mechanic, like is it a cooperative game, card drafting, board game family, expansion, et cetera, et cetera. So there's a lot of really interesting stuff here. I am going to focus on, should we do the category or the mechanic? Let's do the category. It's first. Let's do that one. So let's look at this board game category here, and that's what we're going to use in this modeling. So since we need both of those, let's join those up. I'm going to call it ratings join. I'm going to take my ratings and I'm going to left join with my details by ID, like that. So I've joined them together on this ID, and so we've got all this information here. And now let's do a bit of exploratory data analysis before we jump into our feature engineering and our XGBoost model. So let's first look at the distribution of that average. I already said that. Alpha, like so. So this is a pretty nice distribution. I feel like you never see these where it's like, yes, I'm going to model it. It looks good. So this looks so nice. We're going to model this. We've got the mean and we're going to like model up and down. That's the average, not the Bayes average, right? Yes. Okay, great. I wondered if it was artificially having this nice shape, but no, it looks pretty nice. It looks really nice. Okay, let's, so that's good. And then we can go through and do some more EDA. In the interest of not having this screencast just drag on too long, I am going to, what do I want to do? I'm going to use the mins and maxes. And let's just make like one exploratory plot. Let's, that min age right now is a, is like a numeric value, but let's make some bins, like with cut number, min age. Let's make, 4, just make like a real basic sort of easy to read plot. And then, so let's put, min age, the new, factor we just made. Let's make average, put that on the y-axis, and let's make a box plot. Like that. Yeah, see what that looks like. Okay, so there's NA values. Definitely want to take care of that when we do the modeling. I'm probably, doesn't look like there's that many. I'm probably just going to get rid of them. There we go. Nice. That's pretty good. Yeah. So here's like, oh no, I'm going to get rid of the NAs. Filter, not is NA, min age. Like this. There we go. Okay. So if the minimum age that you can play the game is no minimum to 8, this is the average. And then it looks to me like there is some pretty, I believe that trend looks pretty real, that we've got some slight shifts to higher, ratings for the game, for the board game, if it is intended for older players. So that we see a bit of that trend here. I would probably believe that looks real. Okay, so that's some exploratory data analysis. We could, continue on there and do more, but in the interest of getting started, let's move into modeling. So the first, I'm going to load the Tidy Models meta package. And then I am going to do the part of this process, which I call, or which we like to call, spending your data budget. So we've got a lot of different variables here. Okay, so we've got, oh my gosh, not raging, ratings. Okay, so let's take the name in case we want to look at that later. The average, that's what I'm going to model. Maybe I should do the Bayes average. I don't know. And then let's use one of these tidy select. One of these tidy select functions for selecting things. And let's take everything that is a min or max. So min or max. And then, so see, here's how that works. It takes min players, min playtime, max playtime, min age here. And then let's also take that, whatever that first one was, category. It would be interesting to do with mechanic instead or also as well, but let's do it like this for now. And we know we have some NAs, so what happens if we take them out? That's pretty good. Let's keep that. And then that doesn't take out too many. And then let's split this into training and testing. I'm going to split it, let's do stratified splitting with the average so that we have a kind of balanced in training and testing for the low, medium, and high rated games. And let's call this game split, like so. And then from the split, I'm going to get my training data set. And then, just like this, I'm going to make a testing data set. I need to set a seed because I'm splitting. And let's set another seed and make some resampling folds. This is a lot of data, so I'm going to use, let's call it game folds. And I'm going to do make cross-validation folds. I'm going to do it with a training data set, and I'm going to do stratified sampling again. Okay, so let's do all that. So what we've done, we split our data into testing and training, and we've created resampling folds. These folds are what we're going to use to tune our XGBoost model, and then compare and decide what works best. We are not going to touch the testing data for that. And in each one of these splits, this is how much data is going to be used for analysis, like training, and this is the amount of data that's going to be used for assessment, which is like testing here. All right, so we've spent our data budget. The next thing we need to do is talk about this pre-processing here. So I'm going to use recipes for this. So I'm going to start a recipe. We're going to say we're going to predict the average with everything else. And let's say data equals game train like that. So this starts the process of us doing a our pre-processing. I had that name in there, but that is not a predictor. I kept that in case I want to join that back up to find something later, be able to find something. And so I'm going to change the role of that so that we no longer have 7 predictors. We now have 6 predictors here. Next, I'm going to look at that select board game category, like so. So these are, there's different ways you could do this. These are, like this was probably stored in JSON at some point. I don't think I can probably use JSON Lite to get it out, but it's like it's a list of things and there's overlap, right? Like this is a children's game that's about the economy, and this is a children's game that is like nautical war game deduction. So what would I like to do here? I really would like to have a whole set of indicator variables or dummy variables that's like a set of ones and zeros as to whether it is an economic game or not, or it is a negotiating game or not, or it is a card game or not. So there's a couple different ways you could do this. I am actually going to do it by handling the text and tokenizing that text here. So this is like I'm handling the text, but I'm not exactly handling it like natural language, right? It's more structured. There's gonna be a limited number of things that are here. So let's do that. So the first thing I'm gonna do is I'm gonna tokenize the board game category, like so. And then I will filter to only keep, it looks like there's quite a lot of them, so I'm only going to keep the top 30 most common categories. Like this. So let's only keep the top 30. And then the weighting that I'm going to use is term frequency. So this is probably going to be ones and zeros. Like, is it a card game or is it not? So let's do this. Now, if I have, this is my recipe. Let's see what this looks like. And I can, for example, since I want to see how this is doing, let's do game prep, which is when I estimate this recipe. I don't really need this for the model I'm about to tune. However, I want to check and see, this is a little more complex feature engineering, so I really want to make sure that it works and that I understand what it is that I'm getting out. So I'm going to say game prep new data equals null, which instead of putting in new data, it goes in and pulls out the training data. Okay, so let's see what this looks like here. So this right now, we've got the name still, these numeric things that are about gameplay. This is what I'm going to predict here. And then we've got these. But what it has done right now, it has tokenized so that You know, there's children's game, but it's just tokenized to words, so it has children's here. This wouldn't be so bad. This wouldn't be so bad, but these do seem like they're like structured, like they're like this was the option you were supposed to pick if it's a children's game. So instead of just throwing it in and treating it like natural language that could have been any word at all, let me be a little more careful and do a different kind of tokenizer. So if you go here to step tokenize, there's this option for custom token where what you pass there is a function. And it has to take the character vector and output a list of character vectors. So like, how did you break it apart? How did you break the character vector apart into tokens? So if we go down, 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 and look at the example here, custom token, you make a function of x here, and then you pass that here. So this is just splitting on space. So we're going to make a slightly more complex tokenizer here. I'm going to call it split category. I'm going to put x here, x. And then what happens is, so this just uses base string split. I'm going to use the string R, tidyverse string split. Let me look at that example again. Okay, so here's what we've got. I'm going to split on the commas. How about comma space, like that? And what am I going to do next? Okay, let me see. I'm going to just make a little, let me just get one example so that I can look and see if this is working. I'm just going to take one. I am going to pull out the board game category. There, well, I didn't set a seed, so who knows? Let's call this X for now. I don't want to overwrite anything in scope-wise. Okay, perfect. It has 3 items in it. All right, so if I say X1, and I'm going to split it by a comma. So now I have a list, and it has, so this is like the right kind of thing. And I've got like the bits that I broke it apart into. This one, this one, this one. That's not so bad, but we can clean it up a little bit more so that it looks a little better. It's a little easier. So I'm just going to use string R functions for this. I don't think I can go straight. Since it did break it up into a list, I think I'm going to have to map over it. And so let's say I want a string. I'm going to move all of the punctuation like that. So let's copy this and put 1 in there to test it out. Great, that's already better. Novel base got swashed, but I think I would rather take that over how it looked before. I could be even more careful if I want. Anything else? Let us make it go to lowercase. Whoops, right, there's no X. X1 is what I have. Like that. Yep, I like that. And that seems pretty good. Let me just make one more example one to see if abstract strategy. This one has a space in it. Let's see what happens there. And it's only 1. Let's make sure that this doesn't break. That's pretty good. It means our columns are going to have spaces in them, which it wouldn't be the end of the world. But let's do replace all with a space to underscore. That's probably pretty good. And so this now we pass into custom token like that. So let's run all that. So it's prepping, and all right, so we've got all these. It looks like sometimes there's 2 spaces. Maybe that's because there were 2 punctuation marks. I don't know. So let's do a little more. Let's well, I forget what it's called. A string pad. We'll remove. We'll will add padding, trim will remove it, but there's something else. It's called like, oh, that will never work. Squish, that's what it's called. So what string squish will do is it reduces white space inside the string. So like it replaces 2 with 1. So let's, I mean, we could just add another one here. Map string squish. Whoops. Like so. I think that is probably pretty good. Let's run that and see how it goes. Yeah, that looks pretty good to me. Let me do this, and then we can do stir if we don't like this to be able to see kind of what's going on. This looks pretty good. We've got our name, which we have changed to an ID, so it won't be used in modeling. These numeric things, and then we have these categories that we have set up here. So this looks pretty good. So there's only 30 here. Like I could have kept more. Maybe I will next time. And you can see here that like children's game, it's like 00011. Card game, 0011, blah, blah, blah. So we've got a 1 when it is that kind of game and a 0 when it is not. Okay, so that is our feature engineering. So we're doing a little bit more of custom feature engineering. One of the great things about tidy models is it gives you a lot of options, just that work very well in many situations. And if you need to extend it, you often can with the, optional arguments and making your own functions and things like that. Okay, so let's make a model specification. I'm going to use a boost tree. So this is going to be xgboost. So I'm going to just like set up a handful of these to tune. And then I'm not going to remember what is in boost tree. Let's look here. I know trees are in boost tree, but what else is there? Okay, so trees, let's tune that. Try, let's tune that. Min n, let's tune that. And let's set the learning rate and like kind of bump it up high. So this helps us to fit faster than we would otherwise, but we probably could do better by also tuning this. But I think this will be good. And then you no longer have to say this; it will choose a default for you. But I'm going to put this here just so that we all know we're doing XGBoost. And then what I'm doing here is regression, like so. So if I run all this, what it does is I have set up a model specification. I've said what kind of model am I doing, and what are its parameters. It's hyperparameters here. So now let's put these things together in a workflow like this. So I am going to first pass in the recipe. And so notice this stuff was all just to make sure I was making the choices I wanted to. I don't really need that when I go to train my model, because the workflow will, when I fit the workflow or tune it, it will do that for me. It will estimate those parameters for me. All right, so the recipe and then the model specification. And then what this gives us is a workflow here, which is ready for us to tune it. I am going to, I've done a video on this before, but I am going to use the fine tune package, because when you've got XGBoost, like there's a lot of hyperparameters. I could tune even more than this if I wanted to. And it's not, it is not generally very meaningful when it comes to the, data generating process or whatever, like what these hyperparameters end up at. I just need to find the ones that fit my data best. That's the way boosted trees work. So I am going to do this so that I can do racing. Let me, before I forget, set up parallel processing here, and then, and definitely set a seed here. Okay, so I'm going to use, normally I could do something like tune grid or tune base, but I'm going to do tune race. I'm going to racing, because I'm going to try a whole bunch of combinations of hyperparameters, and I can just throw away the ones that look like they're working poorly at the beginning. So I'm going to use the ANOVA, which is a good option to start with, like a good basic option. I'm going to tune this workflow that I just made. I'm going to tune it on the folds of data, the resampling data. I'm just going to use a default for metrics and whatnot, but I am going to set the grid. I'm going to set it pretty high here so that I'm going to try lots of different combinations of values for trees, mtry and min-n. And then I want to see so that you can see when things, like what it does when it goes here. So I am going to, I'm going to turn this on. So control equals control race verbose this true. So what this will do is it will show us as it's going through whether it is like how many it's throwing away as it goes. So it is like a race. Like we race and see which ones are better, and then we can throw away the ones that are not. So let's get this started here and talk about what it's doing. So mtry comes from the number of columns. So it has to look and see how many columns are there to be able to know what values to tune across, like what values for mtry to tune across. So that's what it's doing now. And then what it's going to do is for these 20 possible model configurations, it is going to, at the beginning, fit them all to all of the folds. And then it is going to see how it did and use an ANOVA to say, do some of them look so bad that I can throw them away and not keep evaluating them as I move forward? So that's what it's going. So let's see. I'd love to at least get one of these showing for you before I pause the video. So let's see if that will do that. So basically all these model configurations are in a race against each other to see which ones are doing better. Well, it looks like it's taking a while. This is a pretty big data set, which is why we're using XGBoost for it. So I think what I'm going to do here is I'm going to pause the video, and then I am going to come back when this tuning is done. All right, we're back. So that did actually take a while. I went and had a snack. But now that we're back, we can see what happened. So because we said, this is the logging that we got. So we're minimizing RMSE, root mean squared error. And and then went through this sort of process right here. It eliminated 6, eliminated 7, 1, 2, and then at the end, we only have 3 candidates at the end. So these are the 3 best performing candidates. Our tuning results look like this, where we have whatever split we analyze this on. And then here, notice how the metrics are different. It scrambled the order of the metrics just for extra randomization. And then notice here, we have a lot of metrics because we evaluated all 20 hyperparameter configurations. But as we go down, we have fewer and fewer metrics because it is not evaluating them all anymore. And so down here, we only have 3 candidates down here at the end. So we did it. We did the tuning, and now it's time for us to understand what happened and where we go from here. So there's a nice plotting function game here, which will show us. This looks pretty. This is a very exciting plot. I know. Here, I'll just close this. But notice each of these is like one of the hyperparameter configurations in the race. And so what's happening here is how far did these get? So I hope you can see in the video. There's one way up here that's, clearly bad, clearly not as good. And then these here are, much better, right? But still worse statistically than these. And then down here at the end, we end up with only 3 that are left here that make it all the way to the end. So out of our 20 hyperparameter configurations, we kind of, tuning XGBoost, like one way to do it is to just kind of throw a lot of stuff and see what sticks. And this is basically seeing what sticks and saving ourselves quite a lot of time by not evaluating all these on all the resamples. Yeah, so we can there's lots of helper functions from Tune to look at our results. For example, this will print out a little tibble showing us the best. Well, there's only 3 left. So it shows us the 3 that are left, which are the best. And notice they're all like so close together in RMSE that we can't really tell a difference there. So, but do notice they all have like quite different configurations in terms of mtry, min-n, etc. And the way XGBoost works is like, you can kind of you move one lever and move the other, and it's not like these are particularly meaningful relative to each other in an XGBoost here. But we have to find the one that works best, and so this is the way to do it. So let's get the one that's best. We can do something, instead that was show best. We can also do select best from our results, and let's choose with RMSE. If we choose R squared, it's it's the same thing. So this is the best one. This is the one that we'll use and move forward with. And so what we can do here is we can take that tunable workflow that we had. Remember this, it says tune here. It doesn't have values in it yet. And what we can do is we can say, I want to finalize that workflow with this. So finalize it with these parameters, and then I'm going to use the function last fit. So, and on last fit, you give it a workflow, which we've piped in, and then you give it the split, the test train split. So what is going on here is we are fitting it one last time, as it says, and what last fit does is a bit of a nice convenience wrapper around fitting one last time on the training set and then evaluating using the testing set. Notice I didn't use the testing set all through here during my feature engineering, during when we were choosing a model. We don't use the testing data until we're done choosing our model. And then so if I call collect metrics on this thing, these are now the metrics on the testing set, not the training set. And these predictions here are the predictions on the testing set. Okay, so how do we do up here? So it got a little bit worse, so maybe, I don't know. It's a bit worse. Like on the testing set, it's a bit worse. So that might be something worth looking into if there's a way to, avoid any overfitting that we did there. But let's just keep this here. It's pretty close and move on. What we're going to do now is we're going to do a couple of different approaches to explainability for an XGBoost model, because if I just look at like the XGBoost model, I can't quickly and easily understand what it's doing. It has 1,700 trees in it, which is so many trees, decision trees, and those are all aggregated up to make a prediction. And so I can't really look at the model and say what, why is it doing what it's doing? But I can use a couple of different approaches for model explainability. So these are going to use non-tidies models packages. And so one of the great things about tidy models is we have set it up so that you can integrate with other tools when it comes to modeling, for example, explainability tools. So let's do 2 explainability tools here. I'm going to take, if I take this, this last object, and if I call extract workflow on it, what this does, workflow, like so. What this does is it goes into this tibble that has the resampling folds, the metrics, etc., and it just pulls out the workflow. So I'm going to take the workflow, and then I'm going to go inside of it and get out the parsnip fit. Oh, you know what? No, yeah, I think this is what I have to do. Can I just do it on the... I actually don't know if this will work or not. Oh, it does. Perfect. It has the parsnip model object inside of it. I can just do so, like so. And I think I'm going to have to use this in the other explainability tool I'm about to do. So let me save it. I'll call this the fit. This is like the parsnip object, like not the feature engineering, but just the model estimation. And so what I can do here is I'll call VIP for variable importance on this fit object. Can't remember. I am going to, yes, I'm going to set a geom for point, and I'm going to bump the features up a little bit because I had quite a lot. So let's look at the, let's look at more than just 10. What did I do wrong? Oh no, it would help if I did that, right? Okay. All right, so let's look at what we have here. So this is variable importance that depends on the tree structures of those 1,000 trees. And it's telling me a measure of the importance. So I don't really get any information about whether it's up or down, high or low, how linear is it? No, I don't get any of that. All I get is like, this is important to the prediction. So for rating these board games, it turns out that the max playing time is the most important predictor for predicting the rating of a board game. After that is the minimum age at which that is recommended for playing. Then minimum players, minimum playtime, max players, etc. And then we go down into these categories, these structured categories that we extracted out of that text that we had. Children's game is the most important category. Then miniatures, then war game, trivia, and so forth. So this is one way of approaching model importance. It uses the structure of the model to be able to pull this out. And notice that it was pretty fast because nothing is getting refit or anything like that. We're not even using data. I'm going to show a different approach, and it is Shapley values. So there's there is a package that does SHAP just for XGBoost, and it is pretty nice to use, in my opinion. And so I think the main function, if I remember right, is SHAP prep. No, prep here. And what this does is it gets this ready. So what we need to tell it's going to compute the Shapley values for us. So we pass in the model, we pass in right, we don't have this, we're looking for that, and then we pass in the data set of predictors that were used here. And it right, so I feel like it has to be a matrix, right? Because XGBoost is expecting a matrix, right? Okay. Okay, so we're gonna put, so our model here, so XGB model is this thing right here that we pulled out. We actually need to pull out the underlying XGBoost object, not the parsnip object. So it's like it is like a, like think of it as like layers, like an onion. So inside of the parsnip model is an XGBoost model. And now we have to pass the predictors here. So remember we had this prepped recipe, preprocessing recipe. I can bake it, right, to get out the I have to pass in some data. New data equals null will get us the training data back. So this is the process training data, the engineer training data, but there's actually other arguments in here, like which columns do I want to bake? I don't have to bake everything, and how do I want it out? And in this case, I want it out as a matrix. I guess I could try this, but let's just use matrix. Okay, so let's add a few things here. So I, in this SHAP prep function only wants the predictors. It doesn't want the outcomes. So let's say has role predictor here. So I'm not going to get the name. I'm not going to get the average. And also, I don't want a tibble. I want a matrix like this. So this is going to print out bananas because of matrix printing in R, so I can just scroll out here forever because that's such a terrible print method. But you can see what I got. I got what I wanted here. So I have a matrix instead of a tibble, and I only have the predictors now. I don't have the other stuff. So let's put this in here, like so. Maybe I'll do this. Like so, and then let's save this. So let's say game Shap, like here. So these are, we're gonna compute Shapley values. So so now it's doing it. It is computing the Shapley values. So notice this is taking quite a bit longer than when we did VIP. So VIP just goes into the existing model you have and uses the structure of all the trees to compute variable importance. Shapley values are much more involved. It is finding based on Shapley, it's Shapley additive, something or other. What's the before? I don't know. Shapley additive explanation. So you're saying, hey, for all of the sets of predictors I have, if I make them in different coalitions, do they move the prediction up or down? Do they like, what can we learn about the behavior of our model kind of by poking at it, by saying, well, what if my input is like this? What does the model do? And so by kind of poking at the model object that we have and seeing what it does, we can understand what it's like. So, this is one of these examples of these black box models that we are not super interpretable on their own, but we can use these interpretability algorithms to learn more about them. It did it. It did it. Good. I wasn't sure what I was going to say after that. Okay, apparently it doesn't print anything out, but we can do things like make plots. So this is often what we do with Shapley values, is like use data visualization to understand our model. So there is a summary plot, right? Yes. And so we just put in our Shapley computations here, and it is going to make us a plot that has quite a bit of stuff on it. So let's wait for this to pop up. You can do it, computer. It is definitely taking a while. There we go. Okay, this is what we want here. So we have, let's wait for it to re-render. This is taking a moment. I'm not sure why. I wonder if something else on my computer is making it slow. There it goes. Okay, so it is ordered from top to bottom about what has the highest Shap values. So the maximum playing time here has this big impact. The minimum play time of the board game. Notice min age shifts from low to high. So things that are more on this end make a higher rated board game. Things that are on this end make a lower rated board game. So it looks like, we can look at the colors here, like min age. When the minimum age for the board game is higher, it tends to have a higher rating. When the minimum age is lower, so games for children, I guess, it is lower. And we can go in here and we see that actually here. So it was in the category children's game, and you can see that it is more to the low side. If it is a miniatures game, it's rated to the high side. If it is a trivia game, it's rated to the low side. If it's a deduction World War II game, that's rated higher. And remember, games can have all of these. So the xgboost model can learn complex interactions between these, like a miniatures game that takes a long time to play, et cetera, et cetera. Okay, so this is a summary plot, and then let's just walk through one more kind of plot here that we can make with Shapley values, and that's a dependency partial dependency plot. So let's do shap plot dependence for partial dependency plot. So we pass in, our thing that computed all the Shapley values for us. And then let me remind myself, shap plot dependence. We then put in, what do we want on our x-axis? So let's say that min age thing there. And then you can also, so if I just plot that, it makes a plot like this. So 0 here is the mean, and then things that are above, push it up higher, and then low. So that's actually pretty interesting. Let's take off that. Let's take the smoothing off. And let's add the histogram. These are pretty nice, I think. Like this. So look at this nonlinear behavior. So this is what you get when you use an XGBoost model, is that you're able to learn not nonlinear behaviors because of the structures, the way the trees work. So we can add more information to this plot, like put on the that min players, like games for big groups versus small groups of people. And then let's yeah. It's too small, I think. I want it to be bigger. Nice. Okay. I think this is pretty interesting. Okay. So first of all, you see this super nonlinear shape, right? Where it's like medium to low to high, and then it turns around, right? So like the highest ratings from age are at min age of like 11 or 12, and then it turns back over. And then this min players thing, you can see we don't see much differentiation on the low ages, but on this high age, we see that the big games for enormous numbers of people tend to be rated lower here, whereas the games for smaller groups of people are rated higher.
All right, so we successfully built features from these characteristics of the board games, and then trained an XGBoost model, which had, maybe okay-ish performance. We were able to, I think, predict the rating of a board game with an RMSE of 0.7. We were able to both use the category information to make a better model, and then we spent quite a bit of time on interpretability approaches for a model like XGBoost, which is not directly interpretable from the structure of the model itself. This is so important in so many contexts. I was really glad to be able to talk about how tidy models can integrate with many of these existing interpretability and explainability packages and approaches. So I hope this was helpful, and I'll see you next time.